The search for superheavy nuclei is dependent on this question. Can a nucleus change its density under conditions of critical Coulomb fields? For this purpose, it will be necessary to irradiate nuclei with heavier particles, such as titanium, chromium, and iron. We will get back to this later. And of course, it will also be necessary to study the nuclei which we already know in greater detail. Before we follow this train of thought, let's look at an experiment that was conducted in relation to the movement towards a neutron deficit. And it could be worth further exploring this direction, since a significant rise is expected to take place here. If at some breakthrough moment we move from a reaction with the evaporation of neutrons to a reaction with the evaporation of charged particles, this will indicate a substantial movement towards neutron excess. For example, if we were looking for isotopes of element 115, not in the reaction of americium and calcium-48, but using curium and calcium-48, and focus not on the emission of 2 or 3 neutrons, but on 1 proton with 2 neutrons or 1 proton with 3 neutrons, we could potentially move toward the 113th element. With these numbers of isotopes, and towards isotopes of element number 112, with 4 mass units. This, of course, can only be accomplished with great difficulty, because the cross-section will decrease approximately 50 times. If the new Xi factory can carry out this experiment, we will be able to observe the process. The same goes for finding heavier elements. Perhaps it makes sense to look not only at the neutron emission, but to try to obtain the 120th element from the 122nd compound by radiating curium with iron with the emission of an alpha particle. As a result, we should obtain isotopes of element 120, possibly including heavier ones. All of these conjectures, of course, run up against the fact that today we get a rather low yield from our reactions. We are already accustomed to obtaining 1 nucleus per month, and are absolutely delighted when we gain 1 nucleus per day. We have adapted all of our installations, equipment, and detectors to work with these low cross-sections. But there are very few of these cross-sections. There is not enough time in one lifetime to investigate everything in detail. So, at some point, it will be necessary to stop and think, how can we progress further? What can be done to expand the scope of our research significantly? And here, it might be good to philosophize a little on the question of how would we set up an experiment if we started it not in 2000, but today? Would anything be done differently? Or wouldn't it? It is safe to say that it would be different because during this time, we have learned a lot about superheavy elements and what synthesis reactions should be carried out to obtain them. We know that a compound nucleus should be obtained and that neutrons should be emitted from there. We recognize roughly what cross-sections would be obtained along with other probabilities. We know where the maximum of these cross-sections for the nuclei energy lies. We can identify the competing channels, that is, the background noise. We know the decay times in microseconds, milliseconds, seconds, even hours. This is all accumulated knowledge that, of course, would guide us to the correct formulation of the experiment and the correct choice of equipment. Furthermore, over the past 15 years, technology has also moved ahead, and mightily so, regardless of the fact that we are studying heavy elements. Current experimental techniques have been refined over the past 10 years. This includes accelerators, plasma physics, detectors, and technologies for producing targets and target materials. Now, if we join these two areas and then formulate how the experiment should be done, I'm confident that we could reach a production rate of about 100 times higher in comparison with what we currently have. And all of this prompted us to think that it was necessary to create new equipment, a new installation that would allow us to reach this goal of increased production by a factor of 100. We are calling it the Superheavy Elements Factory.